In this lecture, we shall continue our discussion on continuous maps. We shall begin by geometrically describing a map which we want to prove is continuous. So let H contained in Rn be the hyperplane So we are looking at those points whose nth coordinate is 0, and let P be the point this point. And finally, let H prime be the plane which is parallel to H and which passes through P. So in other words, it is a set of points x1 up to xn such that xn is equal to 1. So if we make a picture in R2, then this is H, this is the point P, and this is H prime. So consider Rn minus H prime, and we shall define a map phi from Rn minus H prime to H, which we want to prove is continuous. So we define the map as follows. Suppose x is a point in Rn minus H prime. So let's say I take some point here. This is my point x. Then I join my x and p with a straight line. And the straight line is going to meet H at a unique point, which we shall call Q. So join x and p with a line. So there is a unique line which passes through x and p. So this line meets H at a unique point Q. So Q necessarily meets H because x is not in H prime. So we define phi of x to be equal to Q. So we have defined a map from phi from Rn minus H prime to H, and the claim now is the following. Let Rn minus H prime and H have the subspace topology Then the map phi from Rn minus h to h prime is continuous. So let us prove this. So since the image of phi lands in H and H has a subspace topology, from Rn to show that phi is continuous, it suffices to show that phi from Rn minus h prime to Rn is continuous. So recall that here we are using the result that if we have f from x to z is continuous, and suppose the image of f actually lands inside y, and so this is f, it factors as, let's say, f0, I compose f0, so f is continuous implies f0 is continuous, where y has the subspace topology. From z. So we are using this result. So it suffices to show that, so thus, yeah, so let us compute. Let us write precisely what the map phi from Rn minus h prime to Rn looks like. So let us take a point. So let x equal to x1, x2 to xn be a point in Rn minus h prime. So the line through x, passing through x and p, so that is given by, so we take this direction p minus x, we take this vector, and it is, all points on this line are going to be given by x plus t times p minus x. So all points on the line joining x and p are going to be represented by x plus t times p minus x for different values of t. So t belongs to R over here. So what is this? So this implies that now we are looking, so the coordinates of this point are, so this x plus t times p minus x, this is equal to into So this is equal to uh, 1 minus t into x1, 1 minus t into x2, 1 minus t into xn minus 1, and the last one is xn plus t into 1 minus xn. So this is 0. So the point which lies on h, so this point is on h when xn plus t times 1 minus xn is equal to 0, which means that t is equal to xn upon xn minus 1. So this implies that 1 minus t is equal to 1 minus xn upon xn minus 1. There's minus 1 upon xn minus 1. So let t naught be equal to xn upon xn minus 1. Then x plus t naught times uh, p minus x is the unique point on the line which lies on h. So thus phi of x up to xn is this point whose coordinates we know are so it's given here 1 minus t x1 dot dot dot, and the last coordinate is 0. So that's minus x1 upon xn minus 1 minus x2 upon xn minus 1 and so on, comma 0. So notice that 1 upon xn minus 1 is well defined as xn is not equal to 1, as q, this point q, it does not, I'm sorry, not q, this point x is not in the hyperplane h prime. So as phi from Rn minus h prime to Rn, so phi is a map from Rn minus h prime to Rn, and the standard topology on Rn is the same as the product topology it follows that to check that phi is continuous, it suffices to check that when we compose this with the projections, uh, each phi I, which is defined as pi compose phi, so that is phi I of x is just the ith coordinate xi upon xn minus 1 for I lying between 1 and n minus 1, and phi n of x1 x2 up to xn is 0. So we have to check that each of these phi i's is continuous. Each of these phi i's are continuous. So, but the functions xi, well, let's say minus xi, so x1, x2 up to xn goes to minus xi and goes to xn minus 1. These are continuous. These two functions are continuous. And I leave it as an exercise to prove from the definition that these two are continuous. And as xn minus 1 does not vanish on Rn minus h prime. So these are continuous on Rn and therefore they are continuous on Rn minus h prime. And as xn minus 1 does not vanish on Rn minus h prime, so then this implies that 1 upon xn minus 1 is continuous on Rn minus h prime. And then this implies their product, that is minus xi upon xn minus 1, is continuous on Rn minus h prime. And finally, so once again, so it is clear that the constant function functions are continuous. So thus phi n, which is the constant map, phi n is continuous. So which implies that phi from Rn minus h prime to Rn is continuous. And since the image lands in h, this implies that phi from Rn minus h prime to h is continuous. H having the subspace topology. So having proved that this map is continuous, we may restrict it to the sphere Sn minus 1 contained inside Rn. So precisely this is defined as Sn minus 1 is those tuples x1 through xn in Rn such that summation xi square is equal to 1. So I line from 1 to n. So okay, so we cannot restrict it to the sphere, so we can only restrict it to, so the sphere intersected with Rn minus h prime. So let me leave this so it is easily checked. That Sn minus 1 minus h prime is equal to Sn minus 1 minus p. Thus, so when we give Sn minus 1 minus p the subspace topology, thus phi restricts to give a continuous map. So which we again denote by phi. So phi now is okay. So let me restrict write as Sn minus 1 minus p. So this is a map from Sn minus 1 minus p to h. So here are a couple of exercises. Show that phi restricted to Sn minus 1 minus p is bijective. Exercise 2. The map phi from Sn minus 1 minus p to h may be viewed as a map phi from Sn minus 1 minus p to Rn minus 1 given by the same coordinate description as above. As above. So show that well, so okay, so there's nothing to show here. In view of the previous exercise, in view of the previous exercise, this map is bijective. So let psi denote its inverse, set theoretic inverse. Show that psi, which is now a map from Rn minus 1 to Sn minus 1 minus p. So Sn minus 1 minus p has a subspace topology, is a continuous map. So this previous exercise shows that phi restricted to Sn minus 1 minus p is a bijective continuous map whose inverse is also continuous. So definition: let f from x to y be a bijective continuous map. And let g from y to x be the set theoretic inverse of f. If g is continuous, then we say f is a homeomorphism. Obviously, there's a simple remark which I leave it as an exercise. If in this case G is also a homeomorphism. So we will end this lecture with two more exercises. So let f from both are easy, x to y be a bijective continuous map. Show that f is continuous if and only if f of u is open in y when u is open in x. Sorry, show that f is a homeomorphism. A homeomorphism. And the final exercise. So yeah. So using the previous exercise, you can easily do this one, the last one. So let x and y be topological spaces. We fix an x naught in x. So and consider the subspace. So this is x naught cross y. This is contained inside x cross y. These are all points of the type x naught comma y, where y belongs to y. So consider this subset with the subspace topology. Okay. Now consider the map. I x naught. So this is a map from y to this x naught cross y. This is given by y maps to x naught comma y. So you have to show that I x naught is a homeomorphism. So we will end this lecture here.